Good day, everyone. So today we'll be looking at energy quantization. Energy quantization. What is energy quantization? Okay, so without much ado, let's dive into this topic. So when we talk about energy quantization, it's simply defined as the existence of energy in discrete specific amount called quanta. The existence of energy of an electron in a specific amount. Unlike the discovery of Rutherford that say that energy is a continuous process. But no, we have said it in one of our classes that Nebel came to debunk that statement that energy actually is not continuous, but in a specific amount. Now, this specific amount is called the quanta. You can see each of these energy level, okay, has the energy quanta, okay. This way has its own energy quanta, the next shell has its own energy quanta. So you could see this electron moving from one shell to the other. Okay, those shells are called the energy level, and the energy around that level is now what we call the quanta. So by formula, the quanta or the energy quanta is equal to hf, or product of h and f, where the h represents the Planck constant, is a constant value that is 6.626 times 10 to the power minus 34 joule seconds, and then the frequency of the electron. Okay, so that's what energy quantization is about by definition. Now, energy level actually refers to the specific discrete amount that the electron can possess. Okay, now we have different level of energy. We have, look at it, this energy level 1, energy level 2, energy level 3, energy level 4. So the electron can move from one energy level to the other, from one to the other. Okay, it can come from lower energy level to higher energy level, and from higher energy level to lower energy level. Then the lowest energy level is called the ground state. Okay, it's called the ground state, and then this n here represents the electron quantum number. So when the electron quantum number is 0, that means the energy level is at the ground state. Energy level here is now 0, as it is at lowest value when the quantum number is 0. Okay, so that it goes from the lowest energy level to the highest energy level. Okay, now the energy of the energy of an electron on each energy level is written by this formula, where E represents the energy of the electron. E equals to minus 1 over n square r, where the n, we have said it before, represents the electron quantum number, okay, the number of the energy level, and the r is a constant. Now the negative sign there shows that work must be done before an electron can move or can be removed from the atom. So work must be done before an electron can move from one energy level to the other, before it can even leave the atom and move to another energy level. So that's what the negative sign represents in the formula. Okay. Now, aside from that, for us to calculate the kinetic energy required for the electron to move from one energy level to the other, we use this formula, half mv squared, where the m represents the mass of the electron, the v represents the velocity of the electron. Another formula for kinetic energy is ev, where the e represents the charge of the electron, and the v represents the potential difference of the electron. The potential difference in moving the electron from one energy level to the other. Okay, kinetic energy is also synonymous to change in energy level. Like if you say energy level E2 and energy level E1, it's synonymous to what? Kinetic energy. All right. So, and that is equals to HF, like we said earlier. So that's HF, that's the product of Planck constant and a frequency. Again, this is also equals to product of Planck constant, which is h, times velocity of light, which is c, all over lambda. Okay, so this is the old formula that we need to know in solving problem involving energy level, where the lambda there represents the wavelength, of the electron. Okay, having said that, let's now see an example on this formula that we mentioned. Question here says that the change in energy level of an electron in an atom is 6.2 times 10 to the power minus 21 joules. Calculate A, the frequency of the photon, B, the wavelength. Okay, and we are given speed of light, which is c, to be 3.0 times 10 to the power 8 meter per second. We are given Planck constant, which is also a constant value of 6.625 times 10 to the power minus 34 joules second. All right, so let's write our parameters out. Change in energy level is given, this is it, delta E, which represents change in energy level, equals 6.2 times 10 to the power minus 21 joules as given in the question. We have to look for the frequency, okay, that's unknown, and we have to look for the wavelength, okay, which is our lambda. So by formula, change in energy level is equal to product of Planck constant and frequency. And if you make F your subject of the formula here, your F will be change in energy level all over Planck constant. All right. Now our change in energy level is given already, so we substitute the value 6.2 times 10 to the power minus 21, then over, this is actually power, because in the question it is power, so we have it as it's a power minus 21, just like we have the minus 34 to be raised to power minus 34. Okay, so we have 6.2 times 10 to the power minus 21. Okay, let's fix that. So this is minus 10 to the power minus 34. Okay, it's power minus 34. This is actually power. Okay, yeah, it's power. All right, so with power minus 34, and then by the time we simplify this, we have our frequency to be 9.358 times 10 to the power 12 hertz. Second part said we should find the wavelength. Wavelength by formula, we can say that change energy level equals to hc over lambda. Our lambda is our wavelength, making lambda such as the formula here, lambda equals to hc over change energy level. Our h remain our Planck constant, which is 6.625 times 10 to the power minus 34. This is power as well here, minus 34, and this is with the power 8, 10 to the power 8, the speed of light. Okay, so we have, and this is with the power minus 21. Let's correct that so we don't have a wrong on the value on the screen. So now we substituted Planck constant to be 6.625 times 10 to the power minus 34, speed of light to be 3.0 times 10 to the power 8, and change energy level which we are giving elsewhere here into this, and our wavelength, which is lambda, will now be 3.2 times 10 to the power minus 5 meters. Wavelength is measured in meters. Okay, so I will say that, let us see another example on this again. Second question says, an atom excited to an energy level E2, which is minus 12.42 times 10 to the power minus 19 joule, falls to a ground level of energy E0 equals to minus 30.3 times 10 raised to the power minus 19 joule. So we have to calculate the frequency and the wavelength of the emitted photon. Okay, so E2 is given in the question, so writing the parameters out, E0 is also given as written out here. Then the energy level will now be E2 minus E0. So difference of E2 minus E0, okay, will now give us the value 17.88 times 10 to the power minus 19 joules. All right, remember we have to find the frequency and the wavelength, that is F and lambda. So F by formula is change in energy level over Planck constant. And when you substitute the value here, so again here, this is 17.88 times 10 to the power minus 19. So this is power of 19, okay, to power 19, and this power of minus 34. So power of minus 34 is here. Let's see here. Yeah, so this is minus 34, and when we simplify this, we have our value to be, our frequency to be 2.698 times 10 to the power 15 hertz. Second part of the question says we calculate the wavelength, and wavelength by formula is also AC over change in energy level, and when we substitute the value of H is a constant, C is also a constant, as we said in our first example. This power, this is also power, this is also power. Okay. So when we simplify this value, we get our value to be 1.11 times 10 to the power minus 7 meters. That's it. Okay, so that will be the value of the wavelength. Okay, so let's fix this. So this is power swell. So that's the value of the wavelength. So having said that, let's see another example again. It said here that the ground state of hydrogen is minus 26.3 electron volts, and the second state is minus 10.3 electron volts. We have to calculate the wavelength of the radiation if the electron returns to the ground state. Okay, now here our parameter was given to be the ground state energy level, which is E naught, is minus 26.3 electron volts, and the second energy state is given to be minus 10.3 electron volt. We have to find the wavelength, which is our lambda. Now, change in energy level will be delta E, which is E2 minus E naught. So, minus 26.3 sorry, E2 is our minus 10.3. So, minus 10.3 minus, then minus 26.3. And when you simplify this, we have our change in energy level to be 16 electron volt. But by comparison, 1 electron volt will give us 1.6 times 10 to the power minus 19 joule, and we need to convert this to joule because we are dealing with we use this SI unit of joule to solve the problem. So energy level now, converting 16 electron volt to joule will now be 16 times 1.6 times 10 to the power minus 19 joule. Okay, now remember that our main problem is to find wavelength. So wavelength by formula is AC over delta E, and our H and C are usual constant. This minus 34 is power, it also is power, minus 30 is also power. Okay, so when we substitute this value here, we have our wavelength to be 7.76 times 10 to the power minus 7 meters. All right, let's solve one more question and then we'll wrap it up. The last question here says, if the potential difference by which an electron moves is 1.5 kilovolts, calculate the velocity with which the electron moves if the ratio of the charge to mass is 1.9 times 10 to the power 11 coulomb per kilogram. And B, calculate the kinetic energy. So the parameters given here, we are given potential difference, which is sometimes represented with capital letter V, is 1.5 kilovolts. We have to find the velocity. Okay, that's the question. Calculate the velocity here and the kinetic energy. We're looking for velocity that is the unknown. Then we are also given charge, ratio of charge to mass. That means charge, which is E over mass, is given to be 1.9 times 10 to the power 11 coulomb per kilogram. We have to find kinetic energy as well. So kinetic energy by formula is half mv squared, which is still equals to electron volt. Now, if we equate half mv squared with electron volt, we have this. Let's say we are not interested in kinetic energy, we are interested in equating this and this. So we have half mv squared equals to electron volt. Now, when you make v squared, here your subject of the formula, you have 2ev over m. Now, this can still be broken down to be 2v times e over m. This fraction here can be broken to be this, 2v times e over m. Okay, and why are we doing that? Okay, now we know that our voltage is actually potential difference here. That's 1.5 kV. Remember I said P, potential difference, can still be represented with capital V. So that V is this here. So 2 times our voltage, which is 1.5, the kilo there, the K there representing kilo, which is 10 to the power 3, then times our electron over mass, charge over mass is giving us 1.9 times 10 to the power 11. That's why we simplify it this way so that we can bring in this. So electron charge over mass here is now 1.9 times 10 to the power 11. And when you simplify all these, V square will be 5.7 times 10 to the power 14. But for us to get V, we need to find the square root because we need to do away with the square. So we have to square root both sides. And when we square root both sides, our V will be square root of this result. And the square root will give us 2.39 times 10 to the power 7 meter per second. So that's the velocity of the electron. Now the kinetic energy by formula is also electron volt. That means electron times voltage. And one electron we know is 1.6 times 10 to the power minus 19. Then times the voltage, that's our potential difference. Now it's 1.5 kilovolt, and 1.5 times 10 to the power 3. And final result will be 2.4 times 10 to the power minus 16 joule. Alright, so that will be all for today. Thank you for listening. Bye for now.